Hi, my name is Alex Sanchez-Stern, and I'm going to be talking about Passport, improving automated formal verification using identifiers. Now, Emily First is my co-first author on this work, and Timothy Zhao, Jonna Kaufman, Yuri Brun, and Talia Ringer are also co-authors. You're not going to find this paper in the PLDI proceedings because it's actually published at Toplas, but you can find it on their website under the Just Accepted section or in the latest next issue. And this talk is going to be about formal verification, writing mathematical proofs about program correctness to ensure bug-free code. Our contribution is Passport, a new approach to augmenting proof search tools that can prove up to 34% more theorems over the base tool. Formal verification has been used to produce verified compilers, operating system kernels, and even web browsers. And it's been shown empirically that it can produce bug-free programs. So what do I mean by empirically? Well, in 2011, there was this project CSmith, which attempted to test C compilers in a new way. And it tested the verified C compiler CompCert, as well as two industry standard compilers, GCC and LLVM. And what it found was that only CompCert had no wrong code errors, no bugs in it. This is great. So how do we actually make this happen? Well, CompCert is verified in this tool Coq. That's going to be the focus of a lot of our work here. So let's talk a little bit about how verification works in Coq. You start with some thing that you want to prove, like every natural number is greater when you add 1, and you translate it into a formal specification or a formal theorem. This becomes your initial proof state, and a proof progresses like a conversation between the prover and the proof assistant, where the prover, the user, will take actions like tactics, like induction, and the proof assistant responds with responses that can include new goals to prove. Then we can recursively take new actions to prove those goals, and if an action doesn't work well, we can backtrack to a different action. So in practice, proofs are a lot more complicated than the one you've just seen. They involve lots of tactics, lots of precise arguments. And this brings us to our central issue here. The reason formal verification isn't more widespread is that it's really hard. It takes a lot of human labor and a lot of time to produce any of this verified software. So CompCert, the verified C compiler, took 3 person-years to produce, and Cell4, the verified operating system kernel, took 22 person-years. Now this may not seem like a whole lot on the scale of industrial software development, but it's important to note that these pieces of software are actually orders of magnitude smaller than their industrial counterparts because they have, fewer features, they're simpler, they have fewer optimizations. So CompCert is actually 362 times smaller than GCC in terms of lines of code, and Cell4 is 2,000 times smaller than the Linux kernel. So how do we deal with hard things that take a lot of effort as programmers? Well, we try and automate them, and that's what this talk is going to be about. So there's already been some work in automating formal proving. A lot of it is use solvers or other sort of like symbolic methods of automation, but we're going to be focusing on using machine learning to automate these proofs. So you first might ask, why not just use ChatGPT? Ask it about how to prove something and see what it responds with. So using whole language models to generate whole proofs like that has been done in the past with Proofabot 9000 in 2016 and Balder in 2023, which actually used the large language models behind things like ChatGPT. But these models are fundamentally limited because they're missing a big part of what happens in an interactive proof in Coq. See, these models start with a prompt, like the theorem statement, and as a language model, they're constantly looking at what they've generated so far to see what they should generate next. But we know from our talk earlier that it's not just the proof script so far that gives the human prover the information they need to prove something. It's also from the proof states. So there are the other models, like CoqGIM, Tactician, and Proofabot 9001, which take the proof state and use them to predict the next tactic. And finally, there are models like TacTalk, which do both. All of these models, to some extent, need to understand terms in a proof language. They come from the things we want to prove, they become these formal terms, and that's when we actually give our models to figure out what the next tactic needs to be. The hard part about understanding terms is that they're not just keywords or syntax, but they're made up of identifiers. So almost everything in this term is an identifier. And identifiers haven't been used very widely by previous tools, and some totally erase them. So the passport approach is a new method of encoding terms and the identifiers within them with three different mechanisms: category vocabulary indexing, subword sequence modeling, and path elaboration. So let's talk about each of these three mechanisms. The first relies on the fact that there's not just one kind of identifier, but in fact a few different kinds. There are global definitions, identifiers that are defined for the top level. There are local variables, identifiers that have their meaning within a particular scope. And there are constructors, which are kind of like global definitions, but tied to a type and have some special meaning. So our first encoding mechanism is to determine which of these categories an identifier fits into, and then for each of those categories, we use a table mapping them to indexes for the top some number of most common identifiers. So if the identifier is really uncommon, we might just drop it off the table and give it an unknown index, but for our most common identifiers, we can give it one of these indices. And this allows us to connect it to other identifiers with the same name, or other times the identifier appears in different proofs, as well as more generally other uses of that category of identifier. Our next mechanism is subword sequence modeling, where we break an identifier down into its pieces, because the pieces of a name contain a lot of semantic information put there by the writer of the program. By breaking this down, we're able to connect identifiers to other identifiers that are similarly named, even if they don't have the exact same name, but they're made up of similar pieces. This method of breaking things down was first explored in compression and then in neural machine translation, but we're using it in a slightly different context. Finally, we have path elaboration, where we encode the path that identifier has, the place where it was defined, as part of its encoding. And this allows us to connect that identifier to other identifiers from the same module or set of modules, even if they don't share a common name piece. So putting it all together, we take these three categories of identifiers and we encode them with three mechanisms that allows us to have a tree of the encoded nodes, which then, depending on our base model, we can either process using a tree LSTM to get an encoded term, or just use some sort of sequence model. That allows us to take our proof states and get encoded proof terms, which contain all the semantic information about the identifiers that we can pass to our core model to get the next tactic. So the natural next question is, how well does this actually work? Well, to answer that, we needed a corpus of proofs to test it on, and so we worked with CockGym, a standard benchmark for these kinds of proof synthesis tools. It was developed by Yang and Deng in 2019. It has mathematical formalizations, proven correct programs, and Cock automation libraries. It's made up of 123 open source projects, of which we trained on 97 and tested on the other 26. And we wanted to answer a few questions. First, our top level question was, how does adding this identifier information change the results of a base model tool? Second, how many theorems can enhanced models prove combined? And finally, how does each of these encoding mechanisms affect the overall success rate? And how does that interact with each category of identifier? So to answer our first question, we had a few different base models. One is AS Tactic, the model developed as part of CockGym originally, and the other two are TAC and TALK, models that are based on AS Tactic and integrate proof script information. And what we found is that we can significantly improve on all of these models by adding passport information. So adding the passport identifier information proves up to 34% more theorems over the base model. Next, we wanted to know how well these models combine and prove a diverse set of theorems that can lead to more theorem proving overall. And what we found was, by combining all three of the enhanced models, we get a significant improvement, which is even more significant when compared to the proofs found by combining the base models. And finally, if we combine the base models and the enhanced models, we can do even slightly better. So by combining with prior models, Passport allows us to prove 16.9% of the total theorems in CockGym. Finally, we want to know how each encoding mechanism affects the overall success rate, and how that interacts with each category of identifier. So we start with category vocabulary indexing, and note that for these experiments we're going to be using this other model, talk small, as our base model, which is a version of talk with some slightly smaller embeddings that we found produces more proofs in our experiments than talk itself. And we find that by adding category vocabulary indexing, we can prove more than 300 more proofs. And these proofs are distributed across adding them to locals, constructors, and globals. You can see that for locals, the improvement is modest, but still there. So overall, adding category vocabulary indexing proves 33% more theorems than talk small. Next, we want to understand how subword sequence modeling affects these success rates. And we can see that it adds 87 proofs to our total for all kinds of identifiers. But when we look at how it affects the individual ones, we see something a little surprising. So while it improves locals alone, it actually gives us less proofs when added to constructors alone or globals alone. But the total improvement is much greater than the sum of those parts. So we suspect that's because this information allows us to connect identifiers across categories and not just within categories. So overall, subword sequence modeling gives us 7% more theorems proven. Finally, there's path elaboration. So we can see that path elaboration gives us 161 proofs overall, but we see sort of an opposite effect than from subword sequence modeling when we look at individual categories, because constructors and globals each get about 100 proofs when added alone. And finally, locals have no path, so there's no proofs to be added there. So by adding path elaboration, we get 13% more theorems proven. So that's my talk on Passport, which is a new approach to adding identifier information to existing proof search tools that can be used to prove up to 34% more theorems over a base tool. Thanks.